Hello, this is an introduction of the KG-CAIP for Verallia. My name is Lolita Amann. I'm a data scientist at Software Competence Center Hagenberg, and I will explain how this tool works for the use case. First of all, we have implemented quite a few options for the Verallia use case to load and pre-process the data. It is possible to load the data from the feeder line as well as for the shrink wrapping process. It's possible to load any time interval as long as it's available on Karen. You can also load CSV files. You can define the temporal granularity of choice. For example, for the feeder line, a rougher granularity, for example, 10 minutes is more useful. For the shrink wrapping process, it would be maybe 1 or 2 minutes. For the feeder line, we also have implemented the possibility to filter for the entry temperature as well as for the pull rates. And you can look at the data. You have an example on the right side of a visualization of the time series. It's also possible to see histograms or volume plots and so on. Depending on these visualizations, you then can decide which variables you want to include in the model and which ones maybe you should exclude. Once the data is chosen, you can build your knowledge graph. This starts by selecting variables pairs that you think might have a causal connection that you want the tool to test. The tool tests for two kinds of connections, for simultaneous connections and for connections which are lagged. So for example, zone 1 temperatures will influence scope temperatures with quite a big delay. The user defines how strict the model includes or excludes connections that it finds. The user can also define how far back the model looks for lagged influences on the target, and he can choose how the data is pre-processed specifically for the knowledge graph. You then see on the right nodes give you information on how big the lags might be. Ages give you information on what statistical approach was used to recover this connection. The graph is a prerequisite for the Bayesian inference that we do next. We can speed up Bayesian inference quite a bit if we discretize the data. We use Gaussian mixture models for that, and we don't perform equal width binning. Rather than doing that with Gaussian mixture models, we take into account the frequency distributions of the data. So it takes more kind of into account the nature of the data. Once this is done, one of the options we have with Bayesian inference is a root cause analysis. Let's say you encounter a process condition where you have very low scope temperatures and you don't really want that, and also you're not sure why you have that. Below in the table you see 3 scenarios. You encounter very low scope temperature, medium temperature, and very high scope temperatures. And in the table you then see the input configurations that most likely led to this target state in the scope. This is one option. What gives much more possibilities is the what-if scenario testing part of the tool. You see on the typical interface on the right, you have defined earlier what your target is, and here you have all influential variables for this target. And for each influential variable, you have a drop-down menu where you can choose a state, and then given this variable combination of settings, you can test what is my most likely scope temperature outcome. This can also be very useful, for example, if you have a sensor that is not working. Let's say this central scope temperature sensor is not working. You have a model that describes it. then you would enter in the what-if scenario testing interface the current input settings that you have, and you would get out the most likely GOP temperature given your input settings. In that case, it would be 1213 degrees, and you also get the probabilities out. In this case, it would be 0.4, which is quite high, so we have quite a clear result. It's also possible to check in a safe space what happens if you change set points. You can check how you can change the GOP temperature with the smallest changes necessary. You see an example output for that on the bottom left. This is from a different what-if scenario configuration. There we had a baseline temperature of 1207 degrees, and we wanted an increase of 1213 degrees. Here the model proposed changes in zone 2 and zone 3, and it proposed changes, quite small changes, both in increasing the temperature, though it did not say that we should change the temperatures further down the line. It's rather early in the line. It also gives us an idea how likely this configuration is. In that case, we have a clear increase, so it's more it's more likely than what we put in there. Last but not least, it's possible to get forecasts on the data. These forecasts only work for a horizon that is as long as one timestamp. So if you chose a data granularity of 10 minutes, you can forecast your data 10 minutes ahead. The plot below shows in dark blue the measured values that we get for the GOP temperature. The light blue gives us the discretized data, and the red is our prediction over time. So it's quite precise. That is all about the functionalities of the knowledge graph. So we have the possibility of choosing the data, of visualizing it, of getting a causal structure. We can perform root cause analysis, what-if scenarios, and forecasts. There is a second video as well where you can see how we use this framework for the ADAP use case. Other than that, this is the end of the presentation. Thanks a lot for listening.